Good day, everyone. This is the Group Force Report. I am Irma Jane Pagaura, and together with Miss Janice Rose Saba, we will be discussing about one sample test and its four types, namely binomial test, chi-square one sample test, Kolmogorov-Smirnov one sample test, and one sample runs test. This video is the part 1 of our report. I will be discussing here the first two types of one sample test, the binomial test and the chi-square one sample test. But before I start, let me share to you our learning objectives first. So, first, enumerate the different one sample tests. Decide what one sample test to use given a data set and its hypothesis. Examine the chance occurrences of outcomes and repeated trials for a binary variable. Test whether a series of values is random in a population. Examine the difference between an observed sample distribution and an assumed distribution in a population. Run the analysis using digital technology. And lastly, interpret the result of the analysis. So now, let us start. First, let me discuss what is one sample test is. So, the one sample test is a statistical hypothesis test used to determine whether an unknown population mean is different from a specific value. So, one sample test can be used to test for continuous data. Now that we already know what this one sample test mean, let's proceed to its types. So the first one is binomial test. So what is the binomial test? The binomial test, sometimes referred to as the binomial exact test. It is a test used in sampling statistics to assess whether a proportion of a binary variables is equal to some hypothesized value. Now, what are the hypotheses of the binomial test? So the hypotheses for the binomial test are as follows. So the null hypothesis, or the HO, is that the population proportion of one outcome equals to a specific hypothesized value, while the alternative hypothesis, or the H1, is the population proportion of one outcome does not equal a specific hypothesized value. It is also very important to know when to use the binomial test. So the binomial test is used when a binary variable of interest, or a variable that can take only two possible values, example mortality, dead or alive, is being investigated, and you have a hypothesized or expected value with which to compare it to. So the test can only be used when sample size is small compared to the population about which you are trying to make an inference. So let's take a look at this chart. So the binomial test is derived from the binomial distribution, which can be thought of as the distribution that is followed by the number of successes or failures in a certain number n of repeated independent experiments or trials. In more statistical language, we can say that the distribution relies on the value of n and p, or the probability of any trial being a success, and that these are the parameters of the binomial distribution. It is useful to note that as the sample size, or the value of n, increases, the distribution become more symmetrical and converges to a normal distribution. There is also an assumption about binomial tests. So here it is. So it can be easily remembered using the BINS acronym. So B stands for the variable of interest should be a binary outcome, meaning it can take only two values. So for example, a coin toss, heads or tails, the presence of a disease, yes or no, or like what I said earlier, mortality, dead or alive. So this is sometimes also referred to as a dichotomous variable. Next, the letter I. it stands for the observation should be independent, meaning that one observation should not have any bearing on the probability of another. And the next one is the letter N. It stands for the experiment should have a fixed sample size denoted the small letter N. And lastly, the letter S, it stands for all the independent observations should have the same probability of having the outcome. This is similar to the independence assumptions and can be achieved through random sampling. Okay, so to understand the binomial test more, let me share to you an example. So, suppose a population health researcher carries out a small random sample survey to estimate the prevalence or the proportion of a population affected or herpes simplex virus or the HSV, a common viral infection that causes genital and oral herpes. So, members of the sample are selected at random with a total of 20 people selected. So, N is equal to 20, are independent from one another and have the same probability of having the outcome, and with a binary outcome of interest or the presence of the HSV. So now, here are our binomial hypotheses. So our null hypothesis is that the proportion of the survey participants, the 30% with HSV is equal to 20% or 0.2. And our alternative hypothesis, the proportion of survey participants, the 30% with HSV is not equal to 20% or 0.2. So we can thus conceptualize this as a series of 20 independent trials with the proportion of people with the infection P, following the binomial distribution. Suppose in the survey, it was found that 6 or 30% of the 20 participants had HSV. So the probability of a given survey participants having the disease is therefore P is equal to 0.3. Suppose also that a previous survey found the prevalence of the HSV to be 20%, or this could be from the same population or a comparable population. So the researchers use this as the hypothesized value on which to run the binomial test for the current survey proportion. So the next step is to run the binomial test and generate a p-value, which denotes the probability of getting the proportion of people with HSV as extreme or more extreme than what was observed if true p was equal to the hypothesized value. Statistical packages such as Stata, SPSS, or RStudio can be relied upon to generate the binomial test p-value. But for illustrative purpose, the formula is detailed below. So, if we have n independent trials with probability of having HSV being p, we can calculate the probability of the value being the hypothesized number of HSV cases. So, in this case, R is equal to 4 as 20% of 20 is 4. So our R is 4 using the following formula. So by plugging the value into the binomial formula, we get 0.196. The probability of 6 or fewer HSV cases out of 20, the one-tailed test, since our hypothesis of interest whether the observed and hypothesized value differ in any direction. So we would like to generate a two-tailed test, and so we multiply by 2 to get a final p-value of 0.392. So using a significance level of A is equal to 0.05, we fail to reject the null hypothesis because P is greater than 0.05 and conclude that there is no evidence in a statistically significant difference between the prevalence of HSV in the current survey compared with the previous survey given the sample size. Now that we already discussed the first type of one sample test, the binomial test, let us proceed to the chi-square one sample test. So, what is chi-square one sample test? So a chi-square one-sample test is a statistical test that is used to compare observed and expected results. So the goal of this test is to identify whether a disparity between actual and predicted data is due to chance or to a link between the variable under the consideration. So as a result, the chi-square test is an ideal choice for aiding in our understanding and interpretation of the connection between our categorical variables. So a chi-square one sample test or the comparable non-parametric test is required to test a hypothesis regarding the distribution of a categorical variable. So a categorical variables which indicate the categories such as animals or countries can be a nominal or ordinal. They cannot have a normal distribution since they can only have a few particular values. So next is the chi-square test hypothesis. So the null hypothesis, there are no relationship between the categorical variables. If you know the value of one variable, it does not help you predict the value of another variable. While the alternative hypothesis, there are relationships between the categorical variables. Knowing the value of one variable does help you predict the value of another variable. Now, when can we use chi-square one sample test? So the chi-square test can be used to see if your data follows a well-known theoretical probability distribution like the normal or Poisson distribution. And also, the chi-square test allows you to assess your trained regression model's goodness or fit on the training, validation, and test data sets. Chi-square test has two types. The first one is the independence. The chi-square test of independence is a derivable, also known as the inferential statistical test, which examines whether the two sets of variables are likely to be related with each other or not. This test is used when we have counts of values for two nominal or categorical variables and is considered as non-parametric test. A relatively large sample size and independence of observations are the required criteria for conducting this test. So for example, in a movie theater, suppose we made a list of movie genres. Let us consider this as the first variable. The second variable is whether or not the people who came to watch these genres of movies have bought snacks at the theater. So here, the null hypothesis is that the genre of the film and whether people bought snacks or not are unrelatable. If this is true, the movie genres don't impact snack sales. The other type is the goodness of fit. So in statistical hypothesis testing, the square goodness of fit test determines whether a variable is likely to come from a given distribution or not. So we must have a set of data values and the idea of the distribution of these data. We can use these tests when we have value counts for our categorical variables. So this test demonstrates a way of deciding if the data values have a good enough fit for our idea or if it is a representative sample data of the entire population. So for example, suppose we have bags of balls with 5 different colors in each bag. So the given condition is that the bag should contain an equal number of balls of each color. So the data we would like to test here is that the proportions of the 5 colors of balls in each bag must be exact. Now, to understand the chi-square one sample test more, let's have an example. So let's say you want to know if the gender has anything to do with political party preference. So, the poll 440 voters in a simple random sample to find out which political party they prefer, the result of the survey are as shown in the table below. So to see if gender is linked to the political party preference, perform a chi-square test of independence using the following steps. So here is the first step. Define the hypothesis. So our null hypothesis would be there is no link between gender and political party preference. while our alternative hypothesis would be there is a link between gender and political party preference. So let's proceed to step 2. Calculate the exceed values. Now, you will calculate the expected frequency. So, we have expected value equal to total row times column total over total number of observations. So, for example, the expected value for male Republicans is 240 times 200 over 440, and that is equal to 109. So similarly, you can calculate the expected value for each of the cells shown in the table. So let's proceed to step 3. Calculate the 0 O minus E square over E for each cell in the table. So now you will calculate the 0 minus E to the power of 2 over E for each cell in the table, where 0 is equal to observed value, E is equal to expected value. So the fourth and the last step is calculate the test statistic x squared. So x squared is the sum of all the values in the last table. So for example, 0.743 plus 2.05 plus 2.33 plus 3.33 plus 0.384 plus 1 is equal to 9.837. So before you can conclude, you must first determine the critical statistic, which requires determining our degrees of freedom. So the degrees of freedom in this case are equal to the table's number of columns minus 1 multiplied by the table's number of rows. Rows minus 1. So R minus 1 times C minus 1. We have 3 minus 1 times 2 minus 1, and that is equal to 2. So finally, you compare our obtained statistic to the critical statistic found in the chi-square table. As you can see, for an alpha level of 0.05 and 2 degrees of freedom, the critical statistics is 5.991, which is less than our obtained statistic of 9.83. So you can reject our null hypothesis because the critical statistic higher than your obtained statistic. So this means you have sufficient evidence to say that there is an association between gender and political party preference. So that's all for my report. Hope you learned something. So Miss Saba will continue our report. So thank you, and may God bless us all.